today. Okay. And George, good morning. Thank you for being our speaker today. And we can't wait to hear what you have to present.
All right. Well, thank you for inviting me. And good morning, everybody. And I hope I share a little bit of information associated with Artemis campaign. And they call it Artemis campaign because it's made up of different programs. And I'll mention words about that in my presentation. Hopefully, you can see my screen, or at least my first slide.
Yes, we can see it.
Okay, so um, so here's the agenda, and you hear the word trust, and of course, it's used in the Department of Defense when they talk about trust with human and robotic collaboration. You see the word trust in information technology, and it came to me that, okay, what is really, what are we trusting? It's something's not, you don't see those in requirements anywhere, a requirement for trust. But it turns out that it's somewhat of a psychological, well, even in, somewhat of a neuroscience aspect to trust, and people uh, basically have confidence in what they're using, and it actually plays the psychology and the neuroscience is quite interesting. But I didn't get into that in this. I won't get into that in my presentation, but I do want to share with you. Um, how do we establish that trust, even though it's not a per se a requirement, but the trust in crew controls, and crew controls is a vital part of the Artemis program, just simply because now we're going deeper into space. And as we start going deeper into space, we're going to have to rely more on, let's say, artificial intelligence and machine learning and automation and autonomy and all that stuff. And the systems are going to be quite complex, and so therefore the crew controls are going to have to be able to be easier for the astronauts to handle such complex systems. And one of the reasons for that, and I'll mention that later in my presentation. But well, I'm going to kind of briefly go through is the background of going back to the moon, the Artemis computer interface elements. I'm going to discuss four of them. They're the four key ones, and the one that I'm going to focus on is crew controls. Principles of space system human rating requirements. You've heard the term human rating of a spacecraft, and I'll mention what that all entails. It's quite interesting. I was involved with, of course, I started with shuttle.
George,
Yes.
can I? I'm sorry for interruption. Real quickly, the audio. I think something with your headphones. Can you tweak? The audio is very choppy.
Huh. Okay. Stand by.
Okay. Sometimes those headphones have a tendency to have a losing reception or some sort.
Okay. Let me see if sound.
Still choppy.
Still choppy. All right. Let me. Okay. Let me.
I don't know if it would work without headphones if you unplug it.
Yeah, I gotta have the headphones on.
Okay. Okay.
But let's see. Here is only turn off the and maybe help too. And all right, something happened on the on the internet. Can you hear me?
Yes, it's much better right now.
Okay. Can you still see my screen?
So I see your video, but not the screen. I think we lost your screen share.
Okay. Let me
Can you restart it?
reestablish that.
Mm-hmm.
Okay. Can you hear me now?
Yes,
And can
I
you see
can
the
hear,
screen?
but the screen if momentarily was sharing and then again lost.
Okay. Huh.
And looked like for a while before the screen share that your picture was frozen too.
Okay.
Okay, it's
You see it
starting.
now?
Oh, it's coming up. Yes. All good.
Oh, okay. Sorry, technology can be fun sometimes. Oh, all right. So let me just kind of speak. I'm not sure where I left off, but the agenda for today is kind of give a background of where we're going. Probably some of you already know about the Artemis program, uh, and this is just going to be a short description of what that is going to entail. Then I get into the Artemis computer human interface elements, kind of give you a broad 50,000 foot level of what those elements are. But the focus of my presentation is going to be primarily the crew controls, and the crew controls are going to be quite important for future space missions, especially going deeper into space. But the opportunity to test, new technologies and new ways of computer interfaces or human computer interfaces is going to be on the moon. And I'm going to talk about the principles of human rating requirements. And this is uh, I think the real important part, especially of human spaceflight, is how do you human rate a system? And you've heard the terminology, space rated, human rated spacecraft, and all that. And I'll get into a little bit of what that all entails. When you combine the human rated requirements along with other aspects of it, you establish the trust. And as I mentioned previously, and I'm not sure if you picked it up or not because we're having some difficulties here, is that trust is both a neuroscience as well as psychology aspect to it. So, for the astronauts that are going deeper into space, they want to be sure they're confident that the systems are going to operate properly. So, I'll talk more about trust later in my presentation. So we're going back to the moon, and this is part of the Artemis campaign. There, what you see is a picture, somewhat of a phasing approach. If you look at the left-hand side, obviously Earth, we've been doing low Earth orbit for many years. We have station up there that has it's quite a complicated machine. It's got over 350,000 sensors, over 100 computers, and of course, you have a small crew, and the small crew cannot uh, basically maintain that system and keep its eyes on all the various systems, and that's why you have ground control. That's a picture of the ground control there. You got people mission control. You got people in the back room a mission evaluation room that supports the flight controllers. And then you have Russia. So, you have somewhere in the vicinity of 100 to 200 plus people that are basically the eyes and ears of the space station. And going back to the moon, is going to be the proving ground, if you will, and that's where we're going to prove out technologies that ultimately would lead us to go to Mars. And it's the Artemis campaign is somewhat of a dress rehearsal, if you will, of going to Mars. And sometimes the Artemis campaign is called the proving ground. And it's the opportunity to learn what it's going to take to live on another planet. Various technologies are going to be needed in order to make the Mars trip, and the moon is the opportunity to do that. And the nice thing about the moon, it's about 2 or 3 days away in case of an emergency. Once we go to Mars, it's going to be a totally different story. And now the astronauts have to depend on themselves and their systems in order to get over major critical events, a fire or something happens to the spacecraft. It is very dependent on the crew to fix the problems, and they can't depend on mission control. Time delays are going to be quite long. Going to station is only a quarter-second hop in communication time. Going to the moon is about 2 or 3 seconds. Going to Mars is in the 20 minutes, 30 minutes or so, and depending on the location of Mars relative to Earth. So it's going to be difficult communicating with the Mars expedition. So we need to learn better techniques also of communications. And one of the things we're looking at is like, for example, laser communications. That's still in the early technology readiness level development. So the Artemis campaign is comprised of many different programs, and that's why they call it the Artemis campaign, because you got the orbiting gateway station that's currently being designed, the human lander system, which is what I'm working on. It's going to be basically the taxi, if you will, going from gateway or with Orion to put the astronauts in the human lander system and land them down on the ground, and then return them back up to lunar orbit. And of course, you got the Orion spacecraft that's already gone to the moon unmanned. But I think next year we're going to have the Artemis 2 launch mission where you're going to have four astronauts going to the moon. They're not going to land on the moon, but at least they're going to check out and ring out the systems, the environmental life support systems, and things of that sort that factor the human element. And then on the ground, eventually we're going to have extra vehicle activity and human surface mobility activities and missions. Extra vehicle activities is going to be really important, but at the same time, it can be a hazard because these astronauts are exposing themselves to the the moon environment. Of course, moon environment is unforgiving. It has no atmosphere. It's got a 1/6 gravity, and then it gets pretty cold, pretty hot. Now we're going to the South Pole. It gets pretty cold down there. Now up there at the top, I have different, let's say, human rating requirements that feed into the Artemis program. The big one is human rated requirements to Mars 30,030. This one is replacing the what was known as the 8705 human rating requirements document. That document, I think, is going to be retired, and the Moon to Mars is going to have two volumes. One volume is going to the moon, and the second volume is going to be the one that takes us to Mars and how to human rate system to go to Mars, and that's going to be an interesting one, for development. And of course, the stakeholder requirements is obviously very critical as well as far as developing the systems for the human. And of course, it's very environment dependent. If it's it could be a reference mission just for orbiting, or it's a reference mission going to the surface of the moon. So those kind of requirements, stakeholder requirements, also feed into the Artemis Moon program. Then you got the NASA Standard 3001, Volume 1 and Volume 2. These are best practices. These have been, this document has been evolving for several years now, and it's taken from lessons learned from past programs. Volume 1 is more related to the health of the astronauts. Volume 2 is more of the best practices for the hardware, software interacting with the human. And then there is these two new documents that just recently been published and also approved. Is the GUI standard, which basically tries to standardize the graphical user interface, as well as the icon and symbol library too, that goes with that GUI standard. And you can imagine that you have all these different assets out there: the orbiting station, the lander, the Orion spacecraft, the extra mobility vehicles, and you want to have a standard interface. Otherwise, the astronauts have to train in all these different missions, and it's going to be very challenging, if you will. And so there's something called human systems integration that talks about maximizing some of the aspects, the fact of the human element. And I'll say more about that in my presentation about the human systems integration. But one of the factors that's considered is trying to maximize the training so it's easy for them to learn all these systems. It's going to be quite challenging, especially as we go deeper into space. You have different vehicles, let's say on Mars. They're going to have to make it easy. It's going to have to be an easy, or not easy, but maybe an understandable and way of communicating with all these different vehicles, and not having to relearn how that interface is. So the crew control interface is an important part of the Artemis campaign. So just kind of a notional space systems overview of the computer human interface elements. You got the crew control displays right here in the center, and I center that because it's kind of like the focal point of controlling, command and controlling the spacecraft. Imagery is another CHI element that basically provides situational awareness to the astronauts, and certainly it's a video that can be downlinked to the Earth. Lighting, control the lighting for either internal and external. Lighting is also going to play a vital role as we go deeper into space for helping to maintain circadian rhythms. And then you got the audio aspect of CHI elements, and of course the audio is important for verbal communications, whether it's crew to crew or crew to the ground, or the crew from one space vehicle to another space vehicle, or to the people on the moon. And also you got the space system avionics too as well. And the crew controls is basically the one that sends commands to the space system avionics, flight computers, if you will, for the sometimes commonly known as the command data handling system. And of course, at least for near Earth, ground control can also send commands to the space system. But as I mentioned previously, going to Mars is going to be very difficult to provide real-time commanding of a spaceship. And so the crew controls are going to play a vital part of controlling a spaceship that's far, far away. The one other thing about the crew controls is that it's human rated too as well. And let me explain that the human rating certification process right now is done at the vehicle level. However, a lot of the subsystems, and I know this happened on commercial crew program, as well as what we're doing right now in Artemis program, is that we're also basically human rating a lot of the subsystems, if you will. and crew controls is a vital part of a spacecraft. So it's going to be a part of the human process. And it's, the certification of a space system, the launch vehicle is to ensure that when we certify the system, we're saying that it can safely accommodate and transport humans, to other planets, or provide an opportunity for them to do sorties on the moon's surface. And of course, there's we can't get rid of all the risks that are involved with space exploration. But we do have the opportunity to mitigate those risks through doing additional processes, procedures, requirements that accommodate the human needs, capabilities, and limitations. And that's the important part of having human systems integration as part of one of the processes. And so the human rating consists of three fundamental principles. The first principle is to safely conduct the required human mission. These three come from the 8705, but of course now it's the Moon to Mars 30,030. The second one, and this is the one that pretty much encompasses crew controls, is having human interaction, design features, and capabilities to enhance overall safety and mission success. Basically, we're giving the astronauts the tools, if you will, the interfaces that will help them to overcome some potential catastrophic events, or help correct issues. And then the last one is design features and capabilities to safely recover the crew from hazardous situations. So to give you an example of those three fundamental principles of human rating requirements, like for example, design, evaluate, ensure the total system can safely conduct the human mission. The requirements call out for reliability analysis of the system, and subsystems are also analyzed from a reliability standpoint, and cumulatively the whole overall reliability analysis of the spacecraft is part of a deliverable. The other one is fault tolerant to catastrophic hazards. We don't want them to inadvertently press the wrong button or things of that sort, and obviously provide opportunities in the design for detection and enunciation of faults, and whether those enunciations are video or auditorial or both. It's an important factor in having that feature in a human rating spacecraft. And then the second one, human interaction design and features and capabilities for enhancing overall safety and mission success. Some of the requirements called out of that document is monitor, operate, and control the system, and it gives the astronauts the ability to perhaps work around an issue of the spaceship. Tolerate inadvertent operator action. You don't have one button just to fire a rocket. Rather, you have the arm and fire concept of, and sometimes even three concepts of basically exposing the arm switch, press the arm switch, and then you get a notification that now you're ready to execute. So there's a few steps involved in order to basically deal with critical commanding. And then this is going to be really important, like, especially when we go deeper into space and we have a lot of crew autonomy, is to be able to manually override that autonomous systems. And then finally, design features for having the crew recover from a hazardous situation is mission manual abort, or manual parachute or drogue deployed. I know on a commercial crew program, we have the backup to the autonomous parachute and drogue chute automation is if that doesn't work, they go into manual mode. Same thing with the abort for the launch phase of the mission. How do we establish crew controls? Well, first of all, what is it? Okay, so basically, it's providing confidence that the human, the machine, and the interaction and interdependencies between them successfully perform a specific function or a mission, and not just once or twice, but many times. In other words, it's very consistent in its operation. And how is that trust obtained? Well, that's it goes through the human rating certification process. Basically, it's 5 steps or 5 areas. One is the process and standards, like for example, the NPR 7123 for systems engineering, and but now with the human systems integration as part of the mandatory requirement for programs is the human systems integration working with systems engineering. And so you got also the human rating requirements. I have there 8705, but now it's now, as I mentioned, the moon to Mars 30,030, and then the NASA standard 3001. So you got human rated requirements, you got system requirements based on the reference mission, and then the churning goes on in the systems engineering and human systems integration. And then so you verify and validate the system capabilities and performance through using the systems engineering process. And then you flight test the system. And then after you flight test the system, that's when the final certification occurs. It's not until after we've flown the system that we actually certify it for human rating. And the importance of this, obviously, as I mentioned, is more of a psychological aspect of confidence in this system, and for the astronauts, to use the system, but also ensuring that human error has been minimized when controlling a space system. If you look at all these uh, processes that the human rating go through, you think about the Swiss cheese model, and I'm not sure you're familiar with the Swiss cheese model, but basically this was developed by James Reason back in 1990, I think it was, which basically, he said that a hazard doesn't occur by one event, but there's many things that happen, and so you develop barriers. One barrier could be requirements, another one can be design, another one can be safety assessment, another one could be training. And so all these are barriers against a inadvertent hazard or potentially a catastrophic hazard. But nothing's perfect, and there are gaps, there's holes in there. And so there's that situation where all the holes line up, and some inadvertent action that causes a catastrophic event passes through all these barriers and causes the accident. So in the human rating process and establishing crew control trust is basically trying to flesh out all the issues going through all these processes. You got many people involved with the humans rating in terms of certification. You got people in systems engineering, and then also people in human systems integration, all working together to minimize all these gaps, if you will, in the barriers. If you want to call them a barrier of design, of training, of doing safety assessments, hazard analysis, and such. So let me just briefly talk about human systems integration. I don't know if many of you are familiar with this or not. And one of the first things that I was involved with related to crew interfaces was many years ago. I got involved with human factors folks, and we learned, or rather, we found that human systems integration was a big thing in the Department of Defense, but also we needed to we wanted to improve the processes for working with the human element at NASA. So we established a employee resource group that's now retired and has now become the community of practice in human systems integration. But basically, it's very similar to systems engineering. It's interdisciplinary, but it factors the human element into the design of the system. I know from my standpoint as a engineer, at first, my whole focus was designing the best hardware, the best software, but never thought about the human aspect. in the design of the system. And human systems integration is a somewhat of a, I don't want to say forcing function, but it requires to take into consideration the limitations of the human. So you're looking at it from a technical process, ensuring that the hardware and software address part of the human and is part of the systems engineering process. And there's also the management aspect of it, very similar to systems engineering, is to ensure that all the programmatic risk associated with the human has been factored into it. And so what you see here is HSI basically made up of what's called 6 domains, and each one of these domains factors the human element. Of course, human factors engineering, it's pretty much the hub, if you will, of human systems integration. These folks know and understand the limitations and capabilities of the human. Safety folks involved with analyzing systems from associated, with the human, whether it's the hardware, the software, or procedures as well. Maintainability, making sure that the system can be maintained. This is going to be important as we go deeper into space. We can't afford to have systems that are very complicated to repair, because again, it's going to be a very small crew going into deep space. Operations, this is more for ground control, dealing with autonomous systems, dealing with crew procedures and all that, factoring how operations can be maximized, for the crew that's out there in deep space. Obviously, training is important, as I mentioned previously, ensuring that all these systems can be, let's say, easily used and can be repeated and using that even after months of not using that system. So training actually influences design as well. Habitability. You want to make sure that the size of the vehicle and things like egress and ingress are easy for the astronauts. This is going to be important because there's going to be so many systems that may not be enough room for the astronauts. So we're trying to make it as habitable as possible. I think I can tell you the human lander system for SpaceX is going to be quite roomy. It's a big ship. So, they obviously have a good handle on habitability. And so, you're trying to optimize the system from the standpoint of a particular human systems integration domain, but also you're trying to maximize the total system by the interaction and how one thing influences another domain. And so the total system performance is based on the performance of the system as well as the performance of the human with that system. So you, I'm pretty sure you all are very familiar with the V model of systems engineering. I'm not going to go into a whole lot of detail. These are the nomenclatures that are used out of the 7123 NASA Systems Engineering book. And you got stakeholders, expectations, technical requirements, logical decomposition analysis. Basically, this is where the architecture and traits are occurring. Then you come up with a design solution. Obviously, from all the different options, that you eventually come up with one design solution that gets you to preliminary design review, and then if that one, success is successful, then when you go on to a critical design review, going through the implementation, integration, verification, validation, and then transition to the next phase. On the left-hand side is the definition and design, and then on the right-hand side is the realization of a system. Interesting enough, you see the kind of like going upward a hill, and as one colleague of mine told me, the V model is right because the going on the right-hand side is really sometimes a uphill struggle. You have, like for example, verification of a system, and the system fails. Of course, you got to go back to the drawing board, or maybe you don't know how best to verify, the system in a particular environment. And of course validation. Just kind of a quick note, there's a difference between verification and validation. Verification basically says, hey, we built the component correctly, versus validation that we built the right component or the right system. So a little bit of a difference in there, but still part of the realization system. Now, if you add the human systems integration working collaboratively with systems engineering, you have, I have here an overlay of different things, and I'm not going to get into a whole bunch of detail. But while the requirements are being developed, you also have human requirements. As I mentioned, the human rating requirements that are called out in the Moon to Mars 30,030, the NASA standard 3001, Volume 2, Volume 1. From that, you're doing function analysis, task analysis. Task analysis is an important part of human systems integration, and the human-centered design, which basically is an iterative process of trying to maximize the design of a system for the human. And in case of crew controls, it's very important in terms of displays, in terms of crew button layout and things of that sort. So early HITL testing, HITL, HITL, human in the loop testing. You're maturing the design. You're also doing training development. So over here on the left-hand side, you can see somewhat of a let's say a summary, if you will, of what's going on in trying to maximize the crew control or optimize the crew control design. You have the human, the hardware, the software design, and you got the task design for particular task or tasks. And so you're trying to match the human to the hardware software design, but you're also trying to match the human to the task design. The task may require human and computer, or just pure human. And then, of course, the task design and the hardware design are matched to each other. And so collectively, you have an optimized crew control system. Down here is somewhat of a simplistic analysis, or rather, human-centered design approach. Is you're doing an analysis of a task. You do human error analysis, which the terminology human error analysis is kind of misleading. It's not dealing with just uh, dealing with the human making an error. It's actually looking at the system as a whole, that what could cause a human error because of the way things were laid out, or the way the procedures called out on how to operate the system. From that, we do human in loop testing, yes, assess each one of those tests and see what we need to improve, and then we modify the design and go through the whole process again. On the right-hand side, as part of the systems engineering process, but also human systems integration, is doing the environmental testing, radiation, vibration, electromagnetics, thermal, pressure, leak, depress, and repress. All these are not just for the system as a whole, but also the human element involved in seeing, like, for example, in thermal, you have, let's say, a lot of heat loads dumped into the spacecraft. Well, if it gets too hot, it can affect the human in terms of operating a system in a very hot environment. Uh, uh, let's say there's one acoustics. I don't show it here, but acoustics that it can get so loud that it starts to affect the performance of the human. So there's a just a whole bunch of activities going on that I don't show here, but it's basically factoring also the human and not just the system for verification and validation. And so, just kind of a summary. I'm not going to read everything here, but this Venn diagram just kind of basically summarizes the crew control trust. You have the reference mission system requirements. You got the human rating requirements. You've got the human systems integration process and the systems engineering process, all coming together to create a trusted crew control design. And in conclusion, these missions are going to get complicated. It's going to demand, safer, more effective crew controls because the amount of autonomy associated with these systems. And of course, the moon is going to be the proving ground for seeing how we can effectively design crew controls for handling complex, even more complex systems that we have right now on space station. And the crew controls are going to be a vital part of ensuring mission success. The human rating certification process accommodates the human needs and utilizes human capabilities and making sure that the system and subsystems can control hazards and manage safety risks that are associated with human spaceflight. And establishing trust in crew controls is a combination of human rating certification that involves systems engineering as well as human systems integration processes and procedures. And the bottom line is trust will provide confidence to the crew that the crew controls will operate consistently and effectively in the mission. So that concludes my presentation, and I'm going to stop sharing. Hopefully, I stopped sharing.
Yes, you did. And I'm going to
Okay.
allow the sharing. Okay, screen share, start video. So participants can, if there's any questions, please feel free to unmute and ask questions. And I will start with, first of all, thank you so much for presenting. And this was a little unexpected, but very well done presentation, computer-human interface plus the systems integration, the SANI component of that, and pretty much walking through the whole V. So I appreciate, for many, it may have been even a first time hearing a V. And with that, is there any questions in the audience?
Yes, so I have a question. And also, thank you for the presentation. That was very good. It gives you a very good framework of how this can be done and perfected. Can you say a few words about how it is done and with the actual mission that's going on? Does all this happen before you launch, or is some parts of this are going on during the mission after you launch and you're on the way and you do more validation or something like that?
Yeah, that's a good question. The validation part actually continues on even after the certification. Demo 2 was actually the mission that basically provided the human rating certification of the spacecraft. And also the crew controls. And of course, it was somewhat controversial on crew controls because SpaceX uses touch technology for their displays. And I can tell you from firsthand experience that the astronauts were not too receptive to controlling the spacecraft by touchscreen. And like one astronaut told me, he said, "Would you drive a car with touchscreen?" And no, I don't think anybody would. But we were able to, I think, uh, uh, put them at ease that for the most part, the Dragon system uses autonomy, but it can be overridden. The display touchscreen is not used for critical commanding. It's used more for non-critical commanding, turning on lights, turning on bathroom fun motors and things of that sort. The only thing it can do that comes close is it arms the command, but you cannot execute the command on the display. It's done by buttons at the very bottom. So it's a separation of two different actions that have to happen in order to to send a critical command to the spacecraft. So yes, the validation continues on. I can tell you that even after demo 2 and even up into Crew 7, we're still modifying, updating, and tweaking, the system. So it's an ongoing process.
Okay, thank you.
Uh-huh.
I see Ellen has a raised hand. Ellen?
One of the things that I see now is that we really want the quality of human rated systems, but at the same time, we don't want to do the rigor that's involved in human systems. We tend to want to do something that is a little bit simplified. How do you encourage or advocate for the extra expense and rigor that human systems require?
Yeah, that's a good question. And yeah, it's an ongoing process. Yeah, sometimes the funds or the money cost aspect comes into play, or sometimes schedule, and you have to be cautious about the schedule pressures and trying to cut corners and stuff. So, one of the things we've done in Commercial Crew is the uh, commercial partners have been very receptive to hearing lessons learned from past programs, and what worked, what didn't work, and certainly the ones that come to mind that it's a sensitive subject is the Columbia and and the Challenger accidents, and what some of the influential factors that cause those accidents. And so sometimes I mentioned the Swiss cheese model. One of the barriers that I put in there that I did not talk about, that is in the James Reason model, is organizational barrier. And so the organization as a whole has to, it can have holes in it. You have a project manager that's trying to meet cost and schedule, and they want to cut the cost of training. They want to cut the cost for developmental testing. And so it's something that I think, at least at this point in time, I say NASA and the support contractors and such are pushing back have pushed back when they're trying to, I don't want to say cut corners, but try to reduce the rigor that's needed for human rating certification. In the document, it specifically mentions that it's a mindset also. It's not just the processes and procedures, but it's a mindset. And if you have to do 10 tests or 15 tests, you don't want to say, well, no, I can do 2 and verify that 2 of these tests will satisfy the requirement. You have to go back and push back on them and say, well, it may not work. So it's the human part is it's a difficult task. But I have to say that at least in my experience, the commercial partners that we're starting to engage in, not just Commercial Crew, but also in the Artemis program, are at least at this point receptive to understanding what it takes to human rate a spacecraft subsystem.
Kind of speaking of cost savings in that realm, that there seems to be a big push to use virtual reality technologies to for HIDLs, for training, verification, validation. wondering if you have any thoughts about the usefulness versus the risk of relying on virtual reality as opposed to things like mock-ups for things like that.
Yeah, it's you know, it really should be. It's more of I think a combination of the two that you need. You can't simulate every an actual system because the reality comes into play when you actually do a mock-up. And let's say, for example, it looked great in a simulation and design, but you failed to consider certain factors. I know, and I'm not going to mention it specifically. What happened was a design, early design, in one of the commercial partners spacecraft made it difficult for them to get inside the space capsule, uh, and it just wasn't factored into the design. But virtual reality does have its place in training, especially early training, early assessments. But then it's not really until you actually build the actual system that you have confidence in it. And I think it's uh, virtual reality is part of that iterative human-centered design process, if you will.
Thank you.
Mhm.
I wanted to follow up on Josh's question and put just slightly different twist on what ergonomic considerations are taking into account for crew controls and interfaces, and specifically how to minimize the strain during long duration tasks.
I'm sorry, could you repeat the question, please?
So what ergonomic considerations are taking into account for crew controls and interfaces? So for design and implementation, and some of that is virtual reality involved in designing that, just because we cannot use the terrestrial environment is not exactly one-to-one a replacement for what the crew will be experiencing in space, and how the differences, and then and also leveraging the ability to interact with the physical objects in on the ground, and to both to train and design.
Yeah, it's the whole aspect of training and designing for training and designing the systems that are going to be used in the actual environment compared to on the ground is somewhat of a challenge. One of the things about radiation, for example, that I learned is the how it affects the cognitive neurological system of a human. And so, you have a human that trained on the ground with that can respond very quickly to actions that they're given, or fault injection into the system. But if your cognitive abilities are starting to decline because of the environment and being in space and all that, depression, all that, what happens to your performance, human performance? Remember, total system performance is the performance of the system times the performance of the human. And so, the challenge, and I think we're going to be learning more and more about that when we go to the moon, is how virtual reality and those kind of simulations are going to evolve, if you will, over the years. I had an opportunity to listen to Dr. Bunny Dunbar, who is a former astronaut, give a presentation on some of the stuff that they're doing there at Texas A&M, and they're looking at the what's called the digital twin. It's becoming quite popular in terms of the digital transformation, where and I know racing cars you do this quite a bit. They basically create a model of the system, and then they actually implement the system, and they put sensors on the system, and they compare the actual data against their models to improve their models. So that's something that I think we're going to be seeing more and more of, is doing this digital twin development, where we take our models and then we actually implement, and we're going to capture real-time data and improve those models.
Thank you. And one more question, unless anybody else has. This is a very kind of complicated. How does the Artemis program ensures compatibility and standardization across various spacecraft and mission phases in terms of crew controls and interfaces?
It's a tough one. We're running into a few roadblocks here. Like, for example, Orion has already developed their system, right? And so at the same time, you got gateways being developed. You got the human lander system, not just SpaceX, but also now Blue Origin. And then you have all these surface systems that have yet to be designed and developed. Is to try to keep the design within a certain aspect of commonality, and that's I think a big challenge right now that we're looking at, and but the commercial partners are very receptive to and understand the commonality and its importance, especially with all these assets that are going to be out there that the crew members are going to have to use and get into one and control this system and then get out of that system, go into this system and control that system with hopefully crew control that has a similar look and feel, if you will, of all the other ones.
Yeah, the commonality and the interchangeable or the similar interfaces becoming especially important when we have integrated vehicles with visiting vehicles with Orion, or when integrated into a gateway, for instance, or any other future vehicles. And when going or transferring from one spacecraft to a module and then to another spacecraft, and when you have a different interfaces, that could potentially be dangerous, not just confusing, but dangerous.
Yeah, let me give you a quick example. When I was on travel, my colleague got a rental car, and it was a Mercedes, and I forget the model number. But what we're accustomed to for turn signal, the Mercedes uses it for controlling the reverse drive or neutral of it, and so you and then the controls are just there's so many differences between an American car and the Mercedes. It took both of us to try to figure all this stuff out, while trying to drive it, and it was nerve-wracking. So yeah, I have an appreciation for commonality.
Okay, Josh, you have a hand raised.
Yeah, so it's a great point that, as we get further from Earth, this stuff just becomes more and more important, because we have to reduce how much the crew needs to rely on Earth. So I'm wondering if you have any thoughts about, especially as we go forward to Mars, what does mission control look like? What does mission control even do when we get that far?
Yeah, I suspect hopefully by then we're going to have some kind of infrastructure on the moon that mission control will have more day-to-day operations with. At the same time, going to Mars, mission control is going to have, I think, for the most part, very little intermittent interaction with the Mars. So the Mars spacecrafts are basically going to have to have their onboard call it, I call it the onboard autonomous mission control emulator, if you will. And so not quite the HAL 2000, but something like that the astronauts are going to have to depend on in order to operate these complex systems, and you just can't depend on mission control. So it's going to be a challenge, and we're hoping that perhaps things like laser communications, which is still being in development, will hopefully provide opportunities to increase the communication and speed of data between Earth and Mars. After we leave Mars, I'm not sure what else we're going to have out there. We're going to have some Star Trek stuff, tachyon transmission or something like that.
Any other questions, Mike?
Yes, in regard to virtual reality and all the things that Josh and Svetlana were talking about, do you have any thoughts about using AI? We're in the age of AI now, and in the future, it might be that some application of AI could be used to make all the systems in your V diagram much more efficient and make them go a lot more thorough and faster and save money, but mostly to also find errors in the system that we would not have found otherwise. So maybe in the years to come, it would be obvious to use AI in that way. But do you have any thoughts about that?
Yeah, I mean, I think AI is it's an awesome tool to have. And one of the challenges though with the AI, and I mentioned, onboard mission control and having that kind of capability is the challenge again, going back to radiation, that the commercial systems that we use here on the ground, they use AI. They just don't work very well in the deep space environment because of the radiation effects. That's something we're going to have to overcome, and hopefully the commercial sector will take part in that. So otherwise, we're going to have some slow AI. But I agree with you that having AI to clean up, if you will, any gaps and holes that we have in our design through going through the V model is I think it's going to be very beneficial. The important thing is also learning why those holes happen and maybe prevent those. And ultimately we will have systems with very little holes in them. However, there's always the Murphy's Law that anything can go wrong, will go wrong. And so but the more we can reduce and mitigate issues and risk and errors, the more robust the system will be.
Thank you.
Mhm.
And that's why, and thank you, George. That was a great answer. And I just wanted to expand it a little bit and provide a little, I guess, background to even and to your answer and to Mike's question as far as the forward work, that there's a lot to work with AI. The current models are mostly what we see, that they are based on the training that is used a lot of data and the cloud computing. We cannot use the same environment, the same infrastructure in space. Because the connection to or whatever it is, that we do not have an option for that much data to be transmitted back and forth in real time. And then but work is progressing on because we're using Gateway as the testing grounds, as both the verification and validation of various approaches. And one of them is automation using Vehicle System Manager. In future, I do see that there will be more expanded capabilities from what we are planning right now and what we're having right now. I mean, think about all the movies that we have seen, or even our parents have seen, that it was way out of real world and sci-fi realm. And now because we had seen in the movies in the early days when someone would open a flip phone, or someone would look into a stick and talk to that stick, and there will be a response to a stick. Think about the phones that we're having right now, and the computing capabilities within the phones that we have is outnumbers in just about any respect what was computing capabilities of our spacecrafts that were going to in exploring exploring lunar surface. So definitely the technology steps made gigantic steps in progress, and we will see what we do not even think possible, and even in the realm of impossible, will be presented to us in a few years. So with that, thank you, George, so much for your presentation. Computer-human interfaces are extremely important, and as you demonstrated, human system integration and interfaces are also very important. Those two look from a perspective of computer interacting with human, and human HSI, human systems are getting first as a human and then interacting with the machine. So both of those interfaces are extremely important and need to be well designed, well thought through. And that's exactly what you're doing with your pretty much a whole career in putting into a progress one step at the time, one day at a time. And thank you so much for sharing your knowledge. I know that there will be a few members that contacting you because the presentation and the information that you have shared piqued their interest. And so thank you for that, and thank you for interacting with us in the future.
Sure, my pleasure.
And have a good weekend. Have a great weekend,
Likewise.
everyone. We'll see you next Saturday.
Bye.
Bye.
Thank you.